Okay, let's just dive right into this. Welcome to today's explainer, where we're going to take the somewhat abstract world of mathematical ratios and literally map them directly onto concrete geometry. If you've ever found yourself wondering exactly how math connects to the physical spaces all around us, well, you are in exactly the right place.
I mean, really think about it for a second. How do you fit an entire city onto a single piece of paper? Or, actually, let's go the other way. How do you take a tiny, microscopic cell and draw it large enough to see all of its intricate details on a classroom whiteboard? You're essentially acting as a real-world designer trying to solve a tangible puzzle. And the absolute secret to solving that puzzle? It lies entirely in the math of proportions.
So, here's our quick roadmap for this explainer. First, what are scale drawings? Second, visualizing the scale factor. Third, solving with ratios. Fourth, one really common setup error you need to avoid. And finally, a self-check. Let's go.
Section 1. What are scale drawings? Connecting geometry to proportional reasoning.
So this is where we really bridge that gap between abstract numbers and physical shapes. A scale drawing uses proportional relationships to represent an object that's just too large or maybe too small to be drawn at its actual size. And keep in mind, this isn't just about sketching a nice picture, right? Drawing an accurate map or blueprint is entirely based on strict proportional relationships. If your proportions are even slightly off, your building won't stand up, or your map might literally lead you right off a cliff. Moving right along to Section 2, visualizing the scale factor, or understanding the math engine. This scale factor is basically the core tool we use to scale things up or shrink them down perfectly every single time. It is the constant number you multiply by to get from the drawing size to the actual size. And what's really fascinating here is how the scale factor acts exactly like a unit rate in proportional equations. It's just like finding the cost for one single apple so you can figure out the cost for 10. Finding out what one single unit on your paper represents in the real world completely unlocks the entire drawing.
Take a look at this incredibly common map scale. 1 inch equals 5 miles. When you're working with this, I highly recommend just chanting those units aloud to yourself. Seriously, 1 inch equals 5 miles. 1 inch equals 5 miles. Saying it out loud helps anchor those abstract numbers on your page directly to the physical, real-world distances. Every single inch you measure with your ruler is exactly 5 real miles out on the ground.
Section 3, solving with ratios. Let's get into the designer's toolkit. Okay, we've got the theory down, so let's actually shift gears and solve a problem. There are 3 crucial steps you need to follow every time. Step 1, write the given scale, and you absolutely must include the units. Step 2, set up the proportion, comparing the map to reality. And step 3, multiply by your scale factor to solve. Strictly following this exact procedure, step by step, guarantees that your final blueprint or map calculation is going to be perfectly accurate. Let's look at a very specific example, pulled straight from Grade 7 Geometry, Unit 6. The map scale is 1 inch equals 5 miles. Now, 2 points are 3.5 inches apart on the map. What is the real distance? I want you to literally imagine taking a ruler and physically measuring that 3.5-inch distance on your own piece of paper. How do we translate that measurement into reality?
Well, setting up a quick table reveals the answer beautifully. In the top row, we have our scale. 1 map inch is 5 actual miles. Our target map distance is 3.5 inches. To get from 1 to 3.5, we just multiplied by 3.5, right? So we do the exact same thing to our actual distance. We multiply our target map distance of 3.5 by our 5-mile unit rate. And 3.5 times 5 gives us 17.5 miles. That is the real distance between those 2 points.
All right, Section 4, one common setup error. We call this the unit trap. Now that you totally know how to do it right, we really need to pivot to a major setup error that pops up constantly in classroom assessments. Take a very careful look at the difference here. The top equation correctly keeps the units attached. 3.5 inches multiplied by 5 miles per inch equals 17.5 miles. But the bottom equation, it drops the units entirely. 3.5 times 5 equals 17.5 inches. So the absolute crucial point here is that if you drop your units, you lose your connection to reality. The raw math calculation of 3.5 times 5 is perfectly correct, but because the student didn't track their units, they ended up claiming the real-world distance between 2 cities was 17.5 inches. A lack of units completely ruins the whole shebang. And this brings us to a golden rule straight from the St. Paul Grade 7 teacher notes,
Always ask what one unit in the drawing represents in reality. You really should reiterate this to yourself every single time you start a problem. Chanting your units out loud, just like we did earlier, is literally the best preventative tool you have against falling into the unit trap. Okay, Section 5. Your turn. A quick self-check to prove your navigator skills. All right, we have walked through the mechanics, we've covered the pitfalls. Now it's time to prove your brand new designer skills. Here's your Unit 6 practice problem. A drawing uses a scale of 2 centimeters equals 5 meters. If a wall is 8 centimeters on the drawing, how long is the wall in real life? I'll give you just a slight pause here. Mentally calculate it using those 3 steps we discussed. Identify the scale, notice the ratio, and multiply. Okay, let's reveal the answers step by step. First, our scale is 2 centimeters to 5 meters. Second, we look at our drawing measurement, which is 8 centimeters. Notice that 8 centimeters is exactly 4 groups of 2 centimeters. So we just multiply the real-world size by 4. 4 groups times 5 meters gives us a final answer of exactly 20 meters. And this brilliantly illustrates how recognizing proportional groups, rather than just crunching numbers blindly, makes the math incredibly simple and intuitive. So, you've officially mastered 2D scale drawings, but I want to leave you with a really thought-provoking question to chew on. If scaling a flat 2D map uses this simple multiplier we just learned about, what do you think happens to the scale factor when you calculate the 3D volume of a scaled-down building? Think about it. You're dealing with width, depth, and height. Now that's a fascinating geometry puzzle for next time. Thank you so much for joining me on this explainer. Keep asking great questions, and I'll see you in the next one.